All right, did we talk about the number E yesterday at all? No, we didn't do anything. Okay, so let's be honest. All right, so basically we're going to talk about a little bit about this thing called the number E. So first of all, does anybody know why pi is pi? Like, why does 3.14159 blah, 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 blah? Why did that one get this label of pi and it gets a button on the calculator and we like use it for things when like I could come up with another non-repeating never-ending decimal and it gets no special name or no button on the calculator and all this kind of stuff? Why? What is the significance of pi? Why is it there? Koji? Good. So it's a ratio of circumference divided by diameter. So I know you guys will all do this. When you go home today, grab a tape measure, okay, and go around your house and measure circular objects. Okay? I know some of you will be doing this. Okay. So basically, take a circular object, measure the circumference, then measure the diameter. Take the circumference and divide it by the diameter, and given some cushion for human error, approximately do you know what number you're going to get? 3.14. Then pick up another circular object, measure its circumference, measure its diameter, take circumference divided by diameter, and guess what you get? 3.14. It doesn't matter the size of the circle, it has this consistent ratio in every circular object between circumference and diameter. Once people figured this out, it gave us some formulas so that we could find things like circumference from diameter or from radius, because that's related to the diameter, and also the area. But also that's why pi is so significant, right? That's why it actually matters. Not like someone just made it up and gave it a name and said, we're going to use this number, okay? So there's another number that has some significance as well, and it's called E. So it's not a letter, it's a number, okay? So it is the number E. And it's referred to as the natural number. So remember before we talked about going to the bank and investing your money, right? Before we went on break? And we kind of had this formula. Right? And we said if we found the bank that gave us like 10% interest, and you guys were all going to let me know if you ever find that bank, right? Yearly, and if we invested this much, and we saw what would happen over the years, and that this formula is a quick way of calculating it. Then I had mentioned to you guys there were banks that could compound money, right? What did it mean if they were compounding the interest instead of just giving you simple interest? So a simple yearly interest rate means they'll apply the interest per year to your amount. If they're compounding it, then what they're going to do is they're going to look at your money a certain number of times throughout the year and apply the interest to it. They're not going to give you all the interest at once. That would be crazy for them. Okay? So basically, this formula gets adjusted if that happens. So guess what N stands for in this formula? The number of times it's compounded per year. So if I say quarterly, what is N? 4. If I say monthly, 12. Daily, 365. Yeah, point something, right? It's leap years. Okay. So that's basically what would happen. So what happens when they compound your money? Well, they take your rate and they divide it by how many times. So you don't get the whole percentage every time they calculate your interest. You only get a portion of it. But look what it does to the exponent. And then tell her she can call me later. So let's say they were going to compound your money 10 times a year, right? That makes the rate a lot smaller. So if they were giving you a 10% interest rate, but they were going to compound it 10 times a year, when they apply the interest, they don't give you all 10% every time. They do 10% divided by 10, which would just be 1%. So each time you're only going to get 1%. But look at the exponent that that's going to get raised to. Let's say you had left your money in there for 5 years. That used to mean that it would be raised to the 5th power. But now that they're compounding it 10 times a year, what power is this number going to get raised to? 50. So even though the interest rates gets cut down to this much smaller rate, because it's being applied to, a power is being applied to it that's so large, that's what makes it grow faster than if they're just giving the simple interest rate every time. So let's say that I invest $1, okay, in an amazing bank that gives me 100% as my interest rate, okay? If you ever find these banks, let me know, okay? All right, so I'm going to invest $1 in a bank that gives me 100% interest rate, and I'm only going to leave my money in there for a year. All right, so if they only compounded it one time a year, if it was really simple interest and not compounded interest, then the ends would just be ones. And notice this basically turns it into this formula, because if the n is 1, does it really change the rate at all? No. Does it really change the exponent at all? No. So that's how it would look. And how much money would I have after 1 year in this simple interest if I put $1 in and I get 100% return on my investment? $2. So you guys might be laughing, like, Miss Dahl, that's so stupid. $2. Hey, I just doubled my money, okay, for doing nothing. Okay. Granted, I should have probably put in more money, but whatever. I now have $2 instead of 1. Okay. So let's say that I go to a different bank that will compound my money more times per year. So I still take my $1. They're still giving me 100% interest. Still just leaving it in for a year. Let's say they decide they're going to compound it monthly. What do you think is going to happen to the amount? Keeper? You'll multiply 12 times? Okay, we'll see. All right, and so then what if I want to do it daily? They would put this 365 in here. And then let's say one bank was like, you know what, Ms. Dahl, we really want your business. You're a valued customer with your $1. And they decided that they were going to compound my interest 10,000 times throughout the year. Okay. Why are you guys all laughing? Okay. And then this other bank would rather have my dollar so badly, they say, you know what, we're going to top everybody. We'll compound your interest 1,000,000 times a year. You guys don't think this happens in my everyday life? Not if I'm not smart enough to put more than $1 in, right? Okay, so, all right. So let's say these are the situations, okay? What do you think is going to happen to each of the amounts as the situations change? Increase, okay? Like how much do you guys think? A lot? All right, let's check it out. All right, so these groups right here, quick as you can, in the calculator, can you please calculate if it's compounded monthly? Okay, that side of the room. Middle of the room, can you guys please calculate if it's compounded daily? This side of the room, can you please calculate if it's compounded 10,000 times a year? And I'll do the calculation for 1,000,000 times a year since I'm so special and they all want my business so badly. Right? And then once you get it, okay, monthly people, do we have any confirmations over there of an amount? That side of the room? Caitlin? All right, $2.61. Now, you might not think that's a lot different, but remember, that's because I was apparently not that bright when somebody offered me this and I only had $1 to invest. I was either severely lacking in the money department or not that bright, right? But really an extra 61 cents is like 61% of what I originally invested. That's pretty amazing, okay? An extra 61 cents on $1, okay? You might not think so, okay? If it was $1,000,000, that would seem like a lot of money to your total. All right? Okay, what about in the middle, the 365 people? What did we get? All right, so $2.71. We round it money-wise. Okay. All right. Better. All right, what about the 10,000? All right. Better. And I got Are you disappointed? Yes. All right. So what happened here? What we thought would happen did happen. The more times they compound it, we do get more money. But does it forever drastically change? No. At first, there might show kind of bigger leaps, but then all of a sudden, at least if you round it like money to the cent, we're not even seeing a difference in the amount of money. So I don't know if you guys remember this, but before break I said, well, what if a bank compounded my money continuously? Physically seems impossible, right? Everything, even if a computer did it, would take some amount of time to complete. Therefore, how could somebody do something continuously, right? Well, actually possible, and here's why. Exponential functions, which these are, because we're plugging stuff into the exponent, right? Think about if something was growing, it could behave like this, right? It could grow, and it could start growing drastically, and then it could grow a little less and a little less and a little less, until eventually it is growing, but it's basically evening out to this one value, because this might be changing way down here, but is it changing the amount that I'm getting, whether they compound it 10,000 times or 1,000,000 times? No? If somebody comes in and offers, I'll compound it like 20 billion times. That's great. Guess what? This is still the amount of money that I get. Okay? So there is a number. We used all ones on purpose to kind of discover this number. The actual number that I got when I did this, which is probably different than the number that you guys got at some decimal place. Okay? This is the actual number that I got. I want you guys to find on your calculator a place where you see the number E. Yes, I said the number E. Okay. Okay, good. So spot number 1 above the division sign. Everybody go ahead and push that, E, and press enter. Here's what we get. Oops, I'm copying the same one I wrote before. Because they're so similar, I can't. 281. Thanks. I need like personal assistant, Kathy. You're hired. Okay. So if we used all ones, this is the number that approaches. Now, granted, if we invest a different amount or the interest rate changes or the number of years change, those are all going to adjust the number. But basically what's happening is things are getting narrowed down to this number right here. So because that happens, this number, like pi, got a special label. Okay? This number is the natural number, okay? E. Right? Did anybody else find the other place that it shows up on the calculator? The green E is like the letter E, not the number E. Yes? Good. So e to the x. So see next to the number 4, there's a button that says ln on it. Right above ln, there's an e to the x. That's the same e that we just did. It automatically just gives you a spot to type in the exponent. Okay? Is that all right with everybody? So e is a number. Pi is a number. It's about 3.14. E is a number. It's about 2.72. Okay? So don't let it freak you out. It's just a number. All right? Why is this number special? Basically because this is what these types of problems even out to be. Also, this leads us to this new formula that if you want the best interest rate, basically they just say we'll compound it continuously. And they can say that because even though it doesn't seem physically possible, it all kind of evens out to one thing, this E thing. So we get this new formula where E is incorporated. So that is in your note guide here. So the amount of money you have in the bank if the principal is compounded continuously, okay, if the interest rate is compounded continuously, is this formula. So if you can't see it that well, you still have your principal, but instead of doing all that 1 plus the interest rate, this kind of thing, you use the number E, and it gets raised to the power of RT. Okay. Obviously, there's a little more math involved in the derivation from where we were at to here, but at least you now know why E even existed. Okay, so there was this pattern of what everything kind of evened out to. So basically, if they said find the compound interest on a principal of $10,000 at 8% interest in these situations. So how much money would you have if you invested $10,000 at 8% interest and your interest was compounded continuously for 1 year? So because it says these words compounded continuously, that's how you know you want to use the formula where E shows up, because that's kind of the limitation that we reach, that even if we put in a really large number for compounding, it eventually doesn't change and becomes this number E. So we are investing $10,000. We're going to use E because of the continuous compounding. Our interest rate is 8%, and we're doing that for 1 year. Okay. Then you just type that into the calculator. Kind of like with the number pi, you could always approximate something with E, but that's what it would be, an approximation if you didn't use the actual E button, because it's irrational like pi. It's never-ending, non-repeating decimal. So we get $10,832.87. Okay? And depending on how they ask the question, the wording here is a little bit weird. This is the amount of money you would have, so the interest that you earned would have been the $832.87. If it was compounded continuously for 10 years, nothing in our calculation would change except for the amount of time. Would be 10 years. And then that's going to change the amount, obviously, to something more than if we just left it in there for 1 year. So if we do that calculation, we end up with $22,255.41. So a new formula, the number E, kind of treat it like the number pi. They have some things in common. Some people like E better than pi. It's a personal opinion thing. Okay. Are we okay with this? So this is the only real stuff you need to know in section 7.2 that we're focusing on right now in order to complete the homework. So your homework is going to consist of graphing some exponential functions that have some transformations. It's going to consist of a couple of problems where you need to apply this formula, and it's going to consist of a couple of problems where you're just going to do a calculation with E in it. Like literally, you just have to type into the calculator, like E to the 6th power. Okay? Are we okay with the number E and how to use this formula? It's not that different than what we were doing before. You just got to look for that word compounded continuously to kind of differentiate which formula to use. All right, so the big idea we have to wrap our head around today, we're not going to graph it right now, is what is a logarithm, okay? So how many of you, for you guys, logarithm is a new word? This is something I haven't heard before. This is a new concept for me. I think you're speaking a foreign language right now, and I'm a little scared. Okay. All right, so logarithm is new for us. That's perfectly normal. Those other people that didn't raise their hand, whatever, okay? Don't worry. Algebra 2 is supposed to be the first place that you learn logarithm. So if you don't know it, you're not behind, even though half of us raised our hand and half of us didn't. The other half of us had a geometry teacher that showed us something, took a summer class, looked in the book already, something like that, okay? It's not that you missed something in your education, all right? Logarithms are very closely related to exponents. So if you're very good with exponents and exponent rules, then wrapping your head around what a logarithm is will be a little bit easier for you. If you struggle with exponents and exponent rules, you're going to have to put in some extra time and effort to be friendly with the logarithm, okay? All right, so here's the basic idea. I'm going to write some stuff not on here first. All right, if I asked you to write, I changed my mind. Okay. An exponential function or an exponential equation normally, so let me say expression first. If I gave you an exponential expression, it means I was giving you an expression that had an exponent in it. And normally that means that someone gives you a base with an exponent, right? And you learned this back in like pre-algebra or something, what an exponent means. And so you can take a base with an exponent, and then you're able to calculate a result. And your result is whatever the value of that entire power is. So example, in this case, 2 to the 3rd power is worth 8. Okay? All right. Now this is an exponential equation because now all of a sudden I've included what it's equal to. So expression, equation, okay? But the basic idea is here to calculate something that involves exponents, you're given a base and the power on that base. And what you think of as the answer to this is the value of the power. Logarithms are still asking you a question about exponents, but they're rearranging the information. It's like a puzzle. You know mathematicians, we don't want to write out the question every time. We want a word or a symbol that means everything I'm trying to say to you in one package. So instead of me just asking you, what is 2 to the 3rd power, I want to ask you, what power do you place on 2 to get 8? So what power do you place on 2 to get 8? 3. That's what a logarithm does. Okay? So a logarithm is a question about what exponent do you put on the base to get the answer, not here's the base, here's the exponent, calculate the answer. It's kind of just rearranging the information. Okay? So how we would write this same thing in logarithm form is that when someone wrote a log expression, your logarithm would also come with a base. So there's a little subscript attached to the word log, and that's the base. So this is pronounced log base 2. Every logarithm has a base. Without a base, it doesn't exist. What if I just wrote this? Oh, to the third power equals, what's the answer? Can you guys calculate that without knowing the base? No. You also can't calculate a log without knowing its base. So every logarithm has a base. What world are we working in? What base are we working with? So this is log base 2. Then you have to know log base 2 of what? Okay? So from this problem, a log question you would get asked is, what is log base 2 of 8? Because remember, the mystery with a log question is not, what is the value of the power? A log is reversing all the information and asking you, what is the exponent you should put on this base to get 8 as a result? So the answer to a logarithm problem is the exponent you would use on the base. So this information means the exact same thing. I look at these expressions from a person who's done this math over and over again for a long time, right? I look at these expressions, and these relay to me the same information. They include a base, an exponent, a value of the power. The base, the exponent that would be on that base to get the value of the power. They're just asking me the question in a different way, okay? Because they don't want to write out, what would be the exponent that you would use on a base of this to get this value of this power? Instead, they use the word log, okay? So are we okay with understanding what a logarithm is? Yeah? All right, so in a little bit more, probably harder to understand notation, but ways that we might see it more often. Basically, any base to any power comes up with a result. Okay? To rewrite that in log world means your log shares that same base, but they give you the result as part of the problem, and you're calculating the exponent that you would use on that. Okay? All right, so let's run through a couple real quick. We'll come back to that page. Log base 3 of 9. 2. Good. Because 2 is the power you would place on 3 to obtain a result of 9. Okay? So this is equal to 2. Log base 4 of 64. 3. You guys okay with that? 3 is the power we would place on 4 in order to obtain 64. Log base 8 of 1/8. -1. See how if you're really good at exponents, it comes a little faster. If you struggle a little bit with some of your exponent rules, it takes a little bit longer to get there. What power would you place on 8 to turn it into 1/8? We would need a negative power, and the 8's not really changing. It's still like 8 to the first power, so -1. And we'll talk about ways to get these if they don't immediately pop into our head in a little bit. Okay. What about log base 25 of 5? Not 1/5. So 1/5 is what you would multiply times 25 to get 5. But remember, we're looking for the power you would place on 25 to get 5. Cassie? Good. Just 1/2. -1/2 would make it 1/5. Okay, so 1/2, because 25 to the 1/2 power would be like the square root of 25, which would make it 5. And again, don't stress. I'll show you a way in a little bit if this is hard for you about how you can break it down a little bit further to figure these out when they're not immediately popping into your head. Okay? Log base 9 of 1. 3? 0. Good. Log base 12 of 1? Log base like 592 of 1? 0. Okay. Log base anything of 1? 0. And logarithms are defined and restricted to only having positive number bases. Like we talked about with our exponential functions, we don't consider a base of a negative falling into this category of exponential functions like the way we graphed them because they would bounce all over. So logarithms are only defined for us in the world of having positive number bases. We don't use log base 1. Why don't we use log base 1? What would log base 1 of 5 be? No. Is there anything you can put as a power on 1 to get 5? No. What's the only thing you can get if 1 is your base? 1. And what would the answer to like log base 1 of 1 be? Infinitely many solutions? All real numbers? I don't know. Right? Lots of different stuff. Okay? So we don't use a base of 1. We don't use a base of 0 for a similar reason. And then there are some other extenuating let's see. Log base 3 of negative 3. Yep. There is no answer. Why is there no answer? Good. If the base is declared to be positive, which it is for all logarithms, that's how it's defined, is there any exponent that has a property of changing a positive number into a negative value? No. Okay, so not possible. Okay? Log base 5 of 0. What's 5 to the 0 power? 1. So 0 is not the power we can place on 5 to get 0. What do we think? There is no answer again. Because is there any exponent that has the property that it turns a value into 0? There's not. So there's no exponent I can place on a positive base to get 0. So this actually is really important to us. If logs are only defined for positive bases, and these can't happen with any exponent on a positive base, basically we can never calculate the log of a negative, and we can never calculate the log of 0. Okay? All right, so looking back at this page, so log base 3 of 9, we already did that one, came out to be 2. What would log base 5 of 125 be? 3. If it's not popping into your head, I know these are the simpler ones right here than some of the ones that I wrote up. Here's what you would ask yourself. Take the question that I asked you and turn it into a little mini equation you can solve. So for example, if for some reason I'm just sitting there and I'm like, I don't know what log base 5 of 125 is. I know what she's asking me, but I just don't know the answer. If you know what I'm really asking you, you can turn it into an equation and find the answer. So log base 5 of 125 means what exponent do you put on 5 so that it equals 125? Take those words and turn it into an equation. What exponent do you put on 5 so that it equals 125? Okay. This equation is solvable if you can get both sides of the equation to have the same number as the base. So like, I don't know, I'm not going to change this. 5 is not really a power of anything else. But how could I rewrite the number 125 so that it matched the base on the other side of the problem? 5 to the third. Once you have the same base, logically, they have to have the same exponent on them to be equal. So at that point, you can just kind of ignore the bases and say, well, this means that this exponent must equal this exponent. So my solution is 3. This is worth 3. I'm not saying that's the fastest way to do this one, because most of you know 5 to the third power is 125. But we'll see some more complicated ones where it might help. Oh, lots of empty slides. Okay. So take a couple minutes in your group and see if you guys can do some of these. I'll tell Sean never to visit again. Okay. So, all right. So if we struggle with this, how many people see this and an answer pops into their head? Log base 1/2 of 2. Okay. What's the answer you guys are getting? -1. Good. For those of us that don't get it, remember 1/2 to what power equals 2. This is 2 to the first power. This is like 2 to the negative first power. And that power would multiply with the power that's already there. Now that the bases are the same, the exponents must be the same. So if negative x equals 1, then x is -1. So this is -1. If you think you messed up somewhere along the way, rewrite it in exponent form and check if it makes sense. Does 1/2 to the -1 power really equal 2? You should know how to calculate the exponent part of it. Do you get what's on the other side? Okay, and if so, then you probably did a good job. And if not, you're either checking wrong, rewriting wrong, or you need to check your work over here. Okay? All right, so in part B, I would ask myself 4 to what power equals 32? Yeah. Say it again. Sorry, I'm just not hearing you. You're not saying anything wrong. I'm just kidding. 2.5? Okay, so let's see if that works out. So how many people are with him? Like, yeah, I'm good. I know what he's talking about. And how many of you are like, how? A few of us? Good. Okay. That's fine. That's where we're at. So again, we write this. Are we okay with where this is coming from? This is the question I'm asking to get the answer to this. 4 and 32, I really can't rewrite 32 as a power of 4, but 4 and 32 are both powers of what base? 2. So I'm going to rewrite both sides of the equation using 2 as the base so I can get that matching base and set the exponents equal to each other. So 4 is the same as 2 squared, and then don't forget that power of x that's there. 32 is the same as 2 to the 5th. Now that the bases are the same, I know that the exponents must be the same. So 2x must equal 5, which means x is 5 over 2, or 2.5. Okay. Now, if you're just getting them by intuitively thinking through exponent rules, that is awesome. But please do note the method that we're using here, because in some cases, people might just give you this equation to solve, and you should be able to solve it. Okay? So we're really learning two things here. We're learning how to calculate logarithms, and in doing that, we're also exploring how to solve some exponential equations when we can write with common bases. Okay? All right, so part C, how many people have an answer? All right, anybody want to share with us their answer? Just Theo? Theo's feeling confident in the logarithms. Yes. -1/2? Okay, so let's see. All right, so we have 64 to what power will equal 1 over 32? So 64 is a multiple of 32, but 64 is not a power of 32. So I need to think a little bit harder about ways I could rewrite both 64 and 32 with the same base. Koji? You got -5/6. We have two answers going on. -1/2, -5/6. For those of us that are here, how can we rewrite both sides of this equation with the same base? 64 and 32. They're both powers of what? 2. Okay, so 64 is 2 to the 6th, and 32 is 2 to the 5th, but then because I want it to be 1 over 32, it's 2 to the -5th. So then again, once the bases are the same, the exponents can be the same, which means I get that I need this original exponent of -5 over 6. All right? So we're okay with this? Basic idea of what a log is, and then some are harder, and we go through this equation process to solve them. Noah? Uh-huh. We wouldn't necessarily have a way to do it. Here, for us to calculate them, we do need, for example, let's say I gave you guys this problem, log base 3 of 7. That has an answer. There is a power you can place on 3 and get 7. Somewhere between 1 and 2, and I would have to try some stuff to figure that out, right? That one I would not expect you to be able to solve by hand, because then even if I go ask myself 3 to what power equals 7, I'm at a loss because I cannot rewrite both sides with the same base. So at this point, we're still limited. We have learned a logarithm, what it is, what it means, and a way to go through and do it, but we can't do everything yet. We will learn a way to calculate this, and the calculator will help us in doing that as well. Okay? One other thing I want to mention back on the first page. Sorry, you guys, I don't mean to be going back and forth so much. I just keep forgetting. I wanted to talk about this common log idea. So every log has a base, but if you notice, the log button on your calculator just says LOG. You don't get to type in your own base. If you guys push the button, you'll notice that if you just push the button, you get to type in what comes after it, but you don't get to type in a base. You can't calculate a log without a base. It has a base. Okay? Koji? Good. Its base is 10. The reason 10 is considered the common logarithm, our whole number system is based on what? You have the ones place, and then you have the tens place, and then the hundredths place, which is the second power of 10, and then the thousandth place, which is the third power of 10, and stuff like this. So our entire number system is based on tens. So the only button they put on the calculator that that's a lie. There's two buttons. But we'll learn about the other one later. See the other one that says ln that we talked about earlier? That's a log, too. It's a natural logarithm. Oh, natural logarithm. Guess what base that one has? E, the natural number. Oh, okay. So those are the only two that were worthy of getting a button on the calculator. Now, there are ways to calculate log base 3 of 7 on our calculator. We just don't know that yet, and we'll figure that out. But so when you see just log, know that is log base 10 of something, whatever comes after it. So if you write log of 5 on the test, but you mean log base 2 of 5, those are two very different things. Everybody understand that? Okay. All right, the last thing we're going to look at is we are going to graph logs. But we're not going to do transformations with graphing. We're only going to do parent functions. So we're also going to take some problems off of your homework assignment. So for example, in parts A and parts B, part B we'll do the first week of second semester. Okay? We're not going to do it right now. But part A would be fair because part A is just a parent function. Log base 3 of x. No transformations. Nothing horizontally happening to x. Nothing multiplying before the log or being added or subtracted after it, so no vertical transformations. This is a parent function. Are we okay with that? All right. So some things a logarithm has for its graph to understand where these things come from. What could you not take the logarithm of? If logarithm always has a positive base, what did we just discover were our limitations? We can't take the logarithm of negative numbers and 0. So basically, for x right here, I cannot plug in 0 or anything negative. Fair enough? I won't be able to calculate it. Which means my whole graph only consists of plugging in positive x values, so the whole graph exists over here. So in a log graph, we have a vertical asymptote instead of a horizontal asymptote, like in our exponential graphs. Okay? So exponential graphs can't reach 0 or negative, so they have this horizontal asymptote saying, oh, wall here, can't go below it. These graphs have a vertical asymptote because you can't plug in this stuff over here, and they say, you know what, wall here can only plug in stuff over here. Okay? So the whole graph is only going to exist over there. Then there was one coordinate pair that every log has in common. If we go back, I keep saying I won't do this, and then I keep doing this, to the problems that I gave you guys, okay? Which one of these problems could I change the base and it didn't change the answer to the problem? This one, right? Okay? Which means no matter what the base is, so for any parent function, no matter what the base is, if you take the log of 1, you're always going to get 0. Okay? So when I look at my log function, and it has base of 3, it doesn't even really matter that it has a base of 3. Just the minute I see log, I know no negatives or zeros can be plugged in, so vertical asymptote here at x equals 0. And then I know that log of 1 will equal 0, so I for sure have the point 1, 0 every single time. Similar to exponential stuff, just kind of happening in a different direction on the graph, right? Exponential graphs always had y equals 0 as an asymptote, and they all had the point 0, 1. These all have x equals 0 as an asymptote, and they all have the point 1, 0. How to get the other points totally depends on the base, just like exponential functions. Okay? Numbers that I would like to plug in here, personally, I would like to plug in 3, and I would like to plug in 1/3. Why do you think I'm choosing 3 and 1/3 as really good values to plug into this function to establish 2 other points, one on each side of this vertex point? Good, because basically, log base 3 of 3. What is log base 3 of 3? 1. Okay, that's why I picked it. Would 2 have been a good choice? No, awful. Okay, that would be a really bad decision. Okay, you can keep working on it for a really long time, but I'm going to choose 3 and plug it in and be able to quickly calculate that it's 1. I personally also like another point on the other side of my vertex, so when I stretch or compress in certain directions, I have things on each side. That's why I chose 1/3. Because what would be another good number to plug into this function? 9 would be good. Log base 3 of 9 would give me 2, but 9's really far away, and it's on the same side of the vertex as this one. It's not going to really help me know that much more about my graph. So instead, I chose 1/3. What is log base 3 of 1/3? Negative 1. 1/3, negative 1. So this graph looks something like this. It does grow forever, but very slowly, right? You'd have to plug in 9 to get 2. What would you have to plug in to get up to a value of 3? 27, okay? So it grows pretty slowly, right? Right now, notice these points are on this graph with this asymptote. I want you guys to just think for a minute. When we used to graph this exponential graph, it had an asymptote at y equals 0. It had a vertex point like all exponential functions at 0, 1. If you plugged 1 into this exponential function, what would you get? 3. And if you plugged negative 1 into this exponential function, what would you get? So here's some information about our exponential function. Here's some information about our log function. What is the relationship between 3 to the power of x and log base 3 of x? Noah? Good. They are inverses of each other. If you drew both their graphs on the same graph and folded over the line y equals x, you would see they're reflections of each other. You see that they're points, right? The x and y coordinates exchange value, and this makes sense because what is an inverse function supposed to do? Undo what the other one does, right? So if this is my exponential function, and I plug in 1, what does the exponential function do to an input of 1? It turns it into 3 to the first power would be, so I input 1 and it gives me out 3. If I now take that 3 and plug it into this log function, log base 3 of 3 asks you what power do you put on 3 to get 3, and your answer is 1. It totally undoes all the stuff you just did to raise it to a power and strips it back to the original exponent that you plugged in, right? So you plug in an exponent to get a value of a power, but when you plug that value of a power in here, the log question takes you back to the exponent. So it totally undoes what the other one does. Okay, so they are inverse functions of each other. All right, so we're going to adjust your homework a little bit so that you will be graphing parent functions, but you will not be graphing things with transformations until the first week of second semester. Okay? You're growing the same amount yearly, and they just look at it once a year and give you the percentage that you earned and move on to the next year. But then we had mentioned in class that there was something that the banks could do called like compounding. And what did it mean if they were going to compound your interest? Any ideas? What's that? Okay, they take some interest at a certain point and they add more interest. So instead of doing it at like one time a year, like, oh, every year we look at how much you have and we give you a percentage of it and we don't look again until the next year, they look multiple times throughout the year. But let's say your interest rate was 12% and they were going to compound it monthly. So how many times throughout the year would they look at your account and change the value? 12 times. They're not going to give you 12% 12 times throughout the year. Okay? It would work out really well for you and really bad for them. What they will do is take 12% and they'll divide it by 12, and they'll only give you 1%. Okay? But that also means that it's changing this part right here, because this part right here was t before, because when they only looked at your money once a year, the exponent would only be how many years you kept it in. But now if they're looking at your money 12 times a year, for 1 year, that exponent would actually have to be 12 because they calculated it 12 different times in that 1 year. And if they were calculating it 12 times a year and you left your money in there for 2 years, what would the exponent really have to be? 24. So they split up the interest rate, but the exponent gets a lot bigger as they do that. So there's actually a different formula. This one's not in your note guide. You can write it down. I mean, as far as if it's valuable, I will tell you guys that when the math club people walked in yesterday, they said, hey, that's what we're doing in pre-calc honors. Hey, that's what we just went over in calculus. So this will keep recurring if you want to see that. So the only thing that's different in this formula from the previous formula is what? N, where N showed up. So R is being divided by N. That's the interest rate being divided into those pieces. But again, that means that a year doesn't really just mean that they've looked at your money one time. It means they've looked at it however many times they're looking at it per year. So N also multiplies the exponent. So this number gets divided and it becomes a smaller rate, but this exponent can get huge depending on how long they look at it. Okay? So let's say I find the best bank in the world, better than the banks we've been talking about. Okay? Remember, if you guys ever actually find these banks outside of the Miss Dahl's mind in the math classroom, you'll call me and give me a little heads up. Okay? And they're going to give me 100% interest. Okay? But I'm either not that smart or don't have a lot of money on me at the time, so I'm only going to invest $1 in my account. Okay? I know, it's kind of sad. All right, so if I invest $1 in this 100% interest earning account, and I'm only going to keep it in there for 1 year, if this is the simple interest, how many times a year are they compounding? Just one. So notice if you plug 1 in for n, does n even really need to be there? No. A number divided by 1 is just going to be that number. 1 times the number is just going to be that number. That really takes you back to that formula. Okay? And how much money am I going to have after a year in that situation? $2, my original dollar and $1 more. Now, you might think that's not that much. That's because, again, Miss Dahl was either really low on cash at the moment or incredibly not smart and only put $1 into this great investment opportunity. Maybe she didn't believe that people were actually going to give her 100% interest. Okay. Now let's say that this other bank says, you know what, we'll do the same thing. Okay. All of a sudden, all the banks really need some money or something. We'll do the same thing and we'll compound your interest monthly. Okay? So that means this part's all going to be the same. I'm going to keep it in there for a year. But now they're compounding my interest monthly. So N becomes 12. Do you think I will make more than $2 or less than $2? More? Okay. Anybody want to wager how much more? 25%. You think 25%? So like 225 or something like that? All right. We'll find out in a minute. All right, then let's say another place says, oh, daily. Ms. Dahl, please come here. Apparently I'm really popular today. And we will compound your interest daily. Okay. And then this other bank says, yeah, I told you guys I'm very popular. The banks and my $1, they really want my $1 in there. We will compound your interest 10,000 times throughout the year. And then one last bank that really needs $1 says, you know what, give your money to us because we will compound it 1 million times throughout the year. All right. At 100% interest. If I just keep my money in there for a long time and don't put any extra, then eventually you're probably paying out more. These businesses, well, they don't exist, so they don't last very long. All right, so here's the deal. Simple interest, I have $2 in my account after the year. So we want to see what's going to happen the rest of these times. Thank you. All right, so this portion of the room, okay? Can you guys do the monthly calculation, please? Middle of the room, can you guys do the daily calculation, please? This side of the room, can you do the 10,000 times a year calculation? And I'll do the million times a year. And we'll write up our results. Okay, first of all, perspective. How much did Ms. Dahl invest? $1. So seeing an extra 61 cents is really an extra 61% of my investment, which means if I had invested $100, that wouldn't be an extra 61 cents. It would be more like an extra $61. If I had invested $1,000, that wouldn't be an extra 61 cents. It would be like an extra $610. Okay? So a little bit of perspective about my investment and what that means. Okay? So here, definitely worth getting your interest compounded, right? Again, it looks like only an extra 61 cents, but remember, compared to my original $1, that's a pretty hefty amount of my original investment. That's more than half of my original investment, okay, that I'm getting extra by putting it here instead of there, okay? Then you see it increase again. Again, 10 cents, okay, is like 10% of my original investment. If I invested a lot more, that would mean a lot more, okay? So that's still worth it. Then we see it is increasing, but all of a sudden, not as drastically as we might have expected, right? From $2.71 to $2.72, and then $2.72, okay? So what's happening here is what we see with our exponential functions, and it's kind of like there's an asymptote that's like a roof. It is growing drastically for a while, but eventually it just kind of evens out, okay? And it is changing, but it's changing way down here, and it's not really going to affect monetarily the outcome that I see because none of that's going to round that to any higher than that.
So the tall chart
Uh-huh.
does that ever go into a flat line, or is it always steadily increasing?
Kind of depends specifically on the situation. Here, generally when we look at our graphs, it is steadily increasing and getting closer, but eventually closer means like 25 million places from the decimal. Like, that decimal has changed. Okay? So that's what's happening. Now, I picked ones on purpose. This number is special. Okay? It's not just a number. It's special. All right? I promise. Now, what I actually got when I put in a million, if I didn't round it to dollars and cents, yeah, Maybe I just need to listen to you because I think that mine's a lot. Okay, say it again. 2.7182280446. Okay, was this decimal? Right? Now, not every ridiculously long, irrational, never-ending, non-repeating, decimal gets a special label or a special place on the calculator, but we know one that we're very familiar with that does have. What's an irrational number that's special? Pi. Why is pi special? Who chose pi? Why pi? So it has these special properties. It goes on forever. It doesn't end. But why did that number get the label? Why did not 7.169, some other irrational number, get this little symbol that means pi and a button on the calculator and like these kinds of things? It's for circles. What is it specifically? Does anybody know? It is not circumference. Say again. Okay, it's like 22 divided by 7. Well, what did you say? No? Okay, so when you guys go home today, break out the tape measure. Yes? You all have one at home? Okay. I know you guys are going to do this because it's amazing. So you're going to go home, you're going to get out your tape measure in your spare time because you have so much of it. And you are going to find circular objects around your house. Like a can. Yeah, and then with the tape measure, you're going to measure the circumference. Then you're going to measure the diameter. Then you're going to take out your calculator. You're going to take the circumference. You're going to divide it by the diameter. And with maybe a little bit of human error in the measuring department, what do you think you're going to get? Pi. Then you're going to get another circular object, much smaller, much bigger. Doesn't really matter. Measure the circumference, measure the diameter, take circumference divided by diameter. Guess what you're going to get? Pi. So we always think of, circumference is pi times diameter. So we use pi because somebody came up with pi. Well, really, no. Pi was developed because in every circle, when they measured the circumference and divided it by the diameter, they kept getting the same stinking number, so there must be something special about it, right? So it gets this label and pi and then shows up in these formulas about circles. In a calculator, no, but Pi Day is coming up, and I'll show you guys an interesting website. There are some generators on the computer that can generate up to like 100 million digits of pi and stuff like that. Okay? We can search for your ID numbers and see how many digits they are after the decimal, stuff like that. All right, so this number is special too, okay? Because it turns out if you change this, you can change the scenario. You can change the interest rate. You can change how many years you put it in. You can change how much money you put in. But using all ones kind of gives you like, there's something special about this number that it all levels out to, right? So this number is called the natural number, okay? And it is E. It is the number E. I did not misspeak. I know I do often, but it is the number E, not the letter E. So look on your calculator and see if you can find the buttons that contain the number E. Garrett. No. That is like a capital E standing for like energy, yeah. This will always be like a little lowercase italic looking E. Okay. Julia. Max. No. Okay. Yeah, so first of all, it's under pi. Good strategy looking for pi, whoever did that, right? Some special numbers grouped together. So the division sign, okay? See the little lowercase italic looking E there? That's E. Go ahead and push that and press enter. And you should notice that you get that E approximately equal to 2.71828. Okay. That's our number. Right? Amazing. Six and 9? Yeah, it was off. But if you keep getting bigger and bigger, it basically approaches this, like the asymptote idea. Like it's going to change a little bit each time. Okay?
Does it keep going? Like after that?
Yes. So E has the same properties as pi. E is irrational, which means it's a never-ending, non-repeating decimal. Okay? Just like pi. Some people like E better than pi. You can do a little research and see what you think. Okay? It's a personal opinion thing. All right. So with this also comes a new formula, because then a bank could basically tell me, you know what, Miss Dahl, just come to our bank. We will compound your money continuously. So physically, everything takes time. Even if a computer does it, it has to take time to generate the new results, even if it's like milliseconds, okay? So how do you compound continuously? Well, theoretically that seems impossible, but then the possibility becomes with the fact that eventually, did it matter if I plugged in bigger numbers for more times compounding? Eventually just kind of evened out to that one thing, right? So they can use that term because it's all going to even out to this one place that it approaches, and E happens to be this thing that it's approaching. Because mathematically, you would want to know if it's approaching one thing or not. And you'll see a lot in calculus as you explore behaviors of different things, especially in the sciences, that things will behave like we see our graphs behaving. They'll have these increases and decreases, but you want to know if they're approaching one thing at the end, because how else can you use it? If it's growing forever, you might use it differently than if you can figure out what it's approaching, then you might have a use for it, and you want to calculate your calculations based on where it will end up with that approach. Okay? So a lot of science and like higher level math applications, and of course like engineering and stuff like that. All right, so right here is a new formula for you guys. This formula would be used if somebody said they're compounding it continuously. So we didn't derive it completely, but why E shows up in the formula is kind of what we were just looking at. If you plugged in bigger and bigger numbers, you get E. So basically how you would use this is this would stand out in any problem where they say things are compounded continuously. Okay? And in this problem, they say you're going to invest $10,000. Since it's compounded continuously, I know I'm using this formula and not one of the other ones. At an 8% annual interest rate, and here I'm leaving it in for 1 year. Okay. And then I would just go ahead and do this calculation on my calculator. I would do 10,000 times E to the power that is up there. Only thing to be careful about, when you do put in your power, and in this case it's a 1, so it's not really going to make a big difference. But when you do put in your power, make sure if there's more than one thing happening in the exponent, that when you typed it in, all that stuff was actually in the exponent and stuff like that. Okay. So here you should get $10,832.87. Okay. And if you kept that same investment in the same type of account, so same interest, compounded continuously, but this time for 10 years, should be more than that, okay? So basically, do the same calculation with a different exponent. You should get $22,255.41. So is everybody okay with this idea of the fact that compounded continuously is kind of a weird idea, but because we end up approaching one number, we can use this formula that now incorporates that one number of E and do the same types of calculation for this more extreme situation. Okay? Any questions about that? So homework 4 is kind of split into 2 sections. Section 1 is from this section of the book, and you're going to be asked to do these things. Graph exponential functions with transformations, similar to section 1 and what we reviewed yesterday. You're also going to be asked to do some calculator calculations with the number E. Just put it into the calculator. Okay? And then you're going to be asked to do some problems similar to what you see here using this formula. Okay? So that's that whole first part of homework 4 will consist of problems only on those topics. Okay? Josh, did you have a question? Okay. All right. So then let's talk about section 7.3. I have a new graphing here. All right. How many of you guys, when you hear the word logarithm, this is a new thing for you? This is a, I don't know what it is. I don't know how to use it. Okay. Thank you. All right. Don't feel like if you raised your hand just because like less than half of you guys raised your hand, either people weren't listening or willing to admit. Don't feel like you're behind. This is an Algebra 2 topic. It's not discussed until Algebra 2. People that know what a logarithm is at this point, it's one of a few reasons. They either took a class in the summer, they went ahead and read the book or watched some notes online or something like this, or they had a geometry teacher last year that at the end of the year told them some stuff about logarithms. But it's an Algebra 2 topic. You're not behind. Okay? The topic is the same as. It's not the same as, but it is the same as. It's basically all of our exponent stuff just written in a different way. Okay? So if you're really good at exponent rules, then logarithms might come a little bit quicker to you. If you struggle a little more with exponents, then logarithms might be a little more difficult for you. Okay? So basically, a logarithm is a new way to ask a question. So you guys know how mathematicians are kind of lazy, right? They don't want to really ask you really long questions. They want notation or words that kind of sum everything up and mean one thing. So when you guys are given an exponential problem, you're usually given a problem like this. They give you a base, and they give you an exponent, and then you do that calculation. This is something you were able to do in, like, pre-algebra, right? Is this okay with everybody? All right, and then what you do is you do this calculation because you understand what all this notation means, and you come up with an answer. Your answer is the value of this entire power. So I'm using some vocabulary on purpose to make sure you guys keep track of the different pieces. There's a base and an exponent in the original expression, and the answer you get is the value of the entire power. Does that make sense to everybody? So a logarithm is basically like a puzzle. Okay? I want to ask you a new question about exponents in a different way. I don't want to give you the base and the exponent, but my question is still really about exponents. Okay? But instead of saying what is 2 to the third power, I want to ask you what power or what exponent do you place on 2 to get something that equals 8? 3. Okay? That's established here because I know how exponents work and I know what rules they are. But if I, as a math person, want to ask you that question every time, it gets kind of old to have to write out that whole question every time, right? Like, what exponent would you place on a base of 2 in order to obtain a value of a power that is equal to 8? That's annoying, okay? That's a long question. You know math people don't do that, okay? So basically, they've developed a word that means it's asking you that question, and that word is logarithm. So a logarithm is really asking you about the exponent. So what you would see if this was written in exponent or in log form is this. You would see the word log, okay? And attached to every logarithm is a base. The same reason you need a base and an exponent. What if I asked you guys this? Oh yeah, what is it to the third power? What's the answer? Can you calculate an answer to my question? No, because what do you need? A base. What the heck am I raising to the third power, right? Same thing for the logarithms. They don't exist without a base. I have to know what world you're living in, okay? So this is logarithm base what? What are we talking about here? So every logarithm is going to have a subscript with it that represents the base, okay? It's the same thing as the base of the exponential function. But remember, an exponent doesn't give, or a log function doesn't give you the same things as exponents. In exponents, they give you base and they give you exponent, and you do this calculation. When I asked you the question that I said was similar to a logarithm, I still gave you the base, but I didn't give you the exponent. I wanted to know the exponent. So instead, I gave you what you would normally think of as the answer or the value of the power, right? So here, you would say, what's log base 2? That tells me, okay, 2 to what power? And then I tell you what the answer was. 2 to some power equals 8. Tell me what the power is that you place on 2. Okay? So the answer to this log problem would be 3. That's how I would calculate it. Right? So a logarithm is a question about exponents. Okay? It's just asking you to calculate something in a different way. Does that make sense? All right? So written kind of more, I don't know, probably more confusing, but more generically, you always have a base to a power, and they calculate as some value. But in log functions, they don't give you the base and the power. Instead, they give you the base, but they give you what you normally think of as the answer, and your job is to figure out the exponent or the power. Okay? Yes? This is what a log is. But then just like how exponents all have properties, like x to the third times x to the second equals x to the fifth, that means there's got to be a property similar to that, but it works a little bit differently because of what a logarithm is for a logarithm too. So logarithms have their own properties. The main point in learning them is to help us figure out things we couldn't figure out before. So for example, before, how would you solve this problem? 3 to what power equals 7? We could estimate and use a calculator to help us narrow it down. But if that's like some crazy decimal, am I going to figure it out on my own? Probably not. Okay? I could get close, but can't really. Logs can help us figure that out. Because we need something that says what is the exponent, some function of math that asks about the exponent in order to solve a question where the exponent is missing, right? So there's a purpose for it, and our eventual purpose is to be able to solve equations that have logs or exponents that are missing. But we have to learn what a log is first and the couple of properties that we can use with it to be able to kind of maneuver through the equations. No. Okay, so Fletcher's question is there a subscript? So I'm guessing you saw the log button on your calculator. Okay, so your calculator has a log button, and it just violated exactly what I said. I said log doesn't exist without a base, right? And when you look on your calculator, what does the button say? Log. Well, guess what? That is one log. It's the most common one that we use. It's actually called the common logarithm. It actually does have a base, even though it's not written. Anybody want to guess what the base of that is? Will? 10. Okay? Why base 10? So when you just see log, that's really the same thing as log base 10. Why log base 10? What is our entire number system based on? Tens. There's like the ones place, the tens place, the hundreds place, the tenths place, right? Everything is based on powers of 10. So that's why that one gets like I guess this one. Okay, because in our number system, that makes sense. All right? Now, to understand how this works a little bit and why it's not log base 1 or log base 0 like some other people pulled out, let's think about how to calculate a couple of these. So log base 3 of 9. So if you're stuck, it's weird notation. You've got to wrap your mind around it. Good. It's really asking me, what exponent should I use on a base of 3 to get 9? So the answer is 2. Okay. Log base 5 of 125. 3. What power do I base on 5 to get 125? Okay. 3. Now, if you struggle with calculating those, there are some other ways of going out about it. Notice that each time I ask you the question, I'm saying the question with lots of words after I say the log because it's new to you guys and I want you to get that stuck in your brain. That log base 5 of 125 really means what exponent do I place on a base of 5 to get 125? If you're ever trying to figure one out and you hear my question in your head and you get that part, but you just can't figure out the answer, take that question and turn it into equation. What exponent do I put on a base of 5 to get 125? This is a totally solvable equation if, so not solvable, solvable, as far as what we know right now. And that's because in this equation, we can rewrite both sides with the same base. Okay? Number manipulation. Okay? Make them look the way we want to look. We're not going to change what anything's worth. We're just going to make it different. Instead of writing 125, what should I write 125 as? 5 to the third. As soon as I can get the same base on each side of the equation, if I have two things that are equal to each other and they both have a base of 5, they can't have different exponents attached to the 5 or they're not going to end up being equal to each other. So logic at this point tells me, well, then this exponent must equal this exponent, which means that my solution is 3. Okay? I'm pointing this out for two reasons. One, this is a way to solve exponential equations, if you can solve them this way. So it's an important skill on its own. Two, these can get a little harder. I'll show you in a minute. Okay? And some of you are like really good with exponent rules and you just like breeze right through. Oh, you do this. Negative 2/3 is the answer. Other people are going to be like, what? It's negative 2/3. Where'd you get that from? And then that will help you when you're in that arena. Okay? Josh? Like of a different base? There's a formula and we'll talk about that. Yeah. So these you have to be able to do without the calculator. Okay? All right. Oh, before we do these ones are uglier and harder. I'm going to do some easy ones first. Let our mind wrap around. Okay? All right. So base 4 of 64. I'm just quizzing you guys. You can write it down if you want more examples. You don't have to. 3. Remember, it's 4 to what power would equal 64? So 4 to the third power would be 64. Log base 4 of 1/4. Negative 1. Good, because 4 to the negative 1 power. Okay, so some of us right now are like, oh yeah, and some of us are like, huh? Okay, so the people probably writing out like the whole little 4 to what power equals 1/4 is going to help you, okay, so you get a better grasp. Those of us that are like, oh yeah, I know the 4's got to flip over and the negative x, and you have that connection, that's because you have a stronger feel for the exponent rules than other people. It's going to be different for each one of us, right? We all got to be able to do it. How we do it is going to be what varies, okay? What about log base 25 of 5? Not 1/5. 1/5 is what you would multiply times 25 to get 5, but it's not the power you would place on 25 to get 5. Max? 1/2. Good. Okay. Because 1/2 power is really the same as doing what? A radical, right? A square root of whatever number. So 25 to the 1/2 really means square root. And if you're struggling with, did I do it right? Rewrite it in the exponent form and see if it makes sense. This is supposed to mean the same thing as 25 to the 1/2 power equals 5. You should be able to calculate the exponent part. We've already studied our exponent stuff. Is 25 to the 1/2 power really equal to 5? Yeah, because 1/2 power really means square root. Square root of 25 is 5. That's good. Okay, did a good job. All right, what about log base 8 of 1? Zero. What about log base 80 of 1? What about log base like 1080 of 1? 0. Because the only power that for sure turns anything into 1 is 0. So this brings me to some ways that logs are defined. They're only defined. This means they only exist mathematically for us with positive number bases. Okay? So no log base -2 of something. They don't exist. Kind of like when we graph exponential functions. We didn't do anything with a negative base because they behave much differently than what we've been studying. Okay? So logs are only defined. They only exist with positive number bases. We don't use 0 as a base. Why not? It'd be like 0 to what power equals something, and that question most of the time is not going to be answered. There's going to be some mystery of mathematics, right? And we don't use a base of 1, just like we don't use a base of 1 with exponential functions. Why not? Okay, because anything would be 1, but could I ever calculate so this would have infinitely many answers, right? Well, you could put any power on 1 to get 1. And if I change this to anything else, can I even get an answer? No. Okay? So like our exponential functions, we only define it for things between 0 and 1, and then things after 1 that are positive numbers. Okay? All right, a couple more questions for you guys. Log base 9 of 0. Good. Undefined. Because what is this asking you? What power of 9 equals 0? Does any exponent property exist that says, oh, when you put this exponent on it, it turns it into 0? No. So can we turn 9 into 0 with an exponent? No. So that's not a possible calculation. All right? Log base 5 of -5. Say it louder. Good. Not possible. Just like there's no exponent that has the property of taking a positive number base and transforming it into 0, is there any exponent that has a property of taking a positive number base and turning it into a negative number? No. Okay? World complex number system, there might be some other things going on, but not in our real number system. Okay? So both of those are things that are impossible for us to calculate. Okay? So there are some restrictions on what we can calculate with a logarithm. Yes?
Are we going to have negative bases?
No. So logarithms are only defined for positive bases not equal to 0 or 1. Okay? So that's kind of a good thing. Okay. All right, so go ahead and try these problems. Actually, we're going to do them together. Sorry, time-wise. I want to make sure that we finish it. Okay. Log base 1/2 of 2. -1. So some of us are on, how many of us are like, yeah, -1, it's an automatic, maybe a couple steps in my head, but I'm good there. Okay. How many of us are like, please write something out so I understand where you're getting -1? Okay, I'm with you guys. All right. So remember what it's asking you. 1/2 raised to what power would equal 2? 1/2 and 2 could both be written as powers of 2. 1/2 is the same as 2 to the -1 power, and then I can't forget the x. Powers will multiply. 2 is just 2 to the first power. And again, once you see the same base, logically there's no way this equation could be true unless these exponents are equal to each other. So -x must equal 1, or the exponent I'm looking for must be -1. So the answer to this is -1. Okay. What's that? So this equation comes from understanding what the log is asking you. So this base to some mystery power equals this value. Then your job is to try and rewrite both sides of the equation so that you have the same base and then the powers can be whatever you want. So 2 is just 2 to the first power and 1/2 is 2 to the -1 power. Once you have them with the same base, the exponents must be equal to each other for the equation to be equal. So then I can just kind of ignore the bases and just set the exponents equal to each other to see what I get for x. Okay, we'll do it again 2 more times. All right? So first step, log base 4 of 32. Figure out what it's asking you. 4 to what power equals 32? 32 is not a power of 4. It's a multiple of 4. 4 times 8 equals 32. Okay, but it's not a power of 4. What are these numbers? Can both be powers of what? You have an answer, like an all-the-way answer? Okay, we're going to wait because some people need us to walk through. Lots of things. All right, so 4 and 32 are both powers of what? 1 to anything is just going to be 1 still. 2. They're both powers of 2. Okay? 4 is the same as 2 to the second power, and 32 is the same as 2 to the fifth power. Now that I have 2 to some power is supposed to equal 2 to another power, the powers must be equal. So 2x must equal 5, which means 2.5 is what I'm looking for. Okay. Yeah, Emma?
Just write it in fractions, or do you want it in?
I don't care. Either way. Yeah. All right, so last one. 64 to what power equals 1 over 32? Okay, so again, 64 and 32. They are both powers of what? 4. So 64 is 4 to the third, but 32 is not 4. 8? 8 squared is 64, but there's no power of 8 that makes 32. 2? Okay, so it's still 2. So it's really hard to separate, but you guys got to think like writing in powers is different than multiples, okay? So 64 is 2 to the 6th, and 32 is 2 to the 5th, but I don't really want 32. I want 1 over 32. So this is 2 to the negative 5th. And so now that I have the same base, the exponents must be the same. So 6x must equal -5, which means the exponent I was looking for was -5, 6. Yeah?
Does the x, like with the 6x, does that always stay the x?
Yes. Because it's like writing, like 64 is 2 to the 6th, and that is still being raised to the x power, and then those would multiply each other. Okay. Yeah, Victoria?
So it's kind of like, if you have like a fraction, you just flip it over and then whatever, like, 1 over 6 is.
And then remember to use the negative exponent. We okay? All right. So we are going to graph them, but we're not, listen. But we're not going to graph them with transformations until the first week of second semester. So you are only responsible for the parent function graphs. So next week on Thursday, on your 10-question test you're taking on exponents and logs, there will at least be 2 graphing questions, one on exponents and one on logs. The one on exponents could incorporate any exponential graph with any number of transformations because we have gone over that, okay? I'm very limited in what I can ask you with the log graphs. I can only ask you a parent function question. So in other words, I cannot ask you something like this. See? Transformation, transformation, transformation. I can ask you something like this. So the only thing I can change in the problem is the base, because all the different bases are all just different parent functions, okay? So to understand what the most basic graph looks like, we can use some of the things that we talked about previously. I want to go back here just for a minute. Okay, when we were talking about this, which ones of these could not be calculated? These guys, right? That means if a log is defined with a positive base, you literally cannot plug in and get an answer, 0 or any negative numbers, right? So if I'm trying to graph a parent function, and I have log, a positive base, and then after that I'm plugging in x, what can I not plug in for x? 0 or anything negative. Where is my entire graph then going to have to exist? Above the x-axis? I can only plug in for x, no zeros or no negatives. Upper right? So this quadrant's good, you're right. So some of it can be in quadrant 1. And quadrant 4, right? No 2 or 3. So 1, 2, 3, 4, just quadrant 1 and quadrant 4. So in exponential graphs, there was a horizontal asymptote because we could never reach 0 or reach the negatives. Here we can't plug in 0 or plug in the negative, so it's kind of like it's been turned sideways. Okay? So there's an asymptote here. Here is like our wall of like, the graph will only exist on one side of this. We've already established the graph will exist on the right side. Now, just like exponential functions, every log parent function, every single one, has one point in common. Just like in exponential functions, every exponential parent function had a point 0, 1. What does every log function have? 1, 0. Because log base anything of 1, what power do you place on any positive number to get 1? 0. So if 1 is the x, 0 has to be the y every time. So they all have this point. So, okay. Every parent, oh, yeah. Okay, now, to get the other points, just like with the exponential ones, I'm going to choose some things to plug in. There are some smart things I can choose and some not so good decisions that I could make to try and plug in here. Given that this one says log base 3 of whatever I plug in, what would be good numbers to plug in for x? 2? Do you guys know what log base 3 of 2 is? No. 9 would be an okay number. 27. 3 would be a good number. Okay, I'm going to use 3. What is log base 3 of 3? 1. Okay. Now, I could plug in 9 and get 2 and 27 and get 3. The only thing that bugs me a little bit about that is if this is like the vertex, right? I like a point on this side and on this side because then when we do certain stretches and compressions, right, it gives us a little more information about the graph. What would be a smart number between 0 and 1 that I could plug in? 1/3. What is log base 3 of 1/3? Negative 1, because negative 1's the power that will just flip it over to the reciprocal, right? So a log graph, it's like this. Yes, it does grow. There's not another asymptote here. It just grows really slow. Okay? It's got to go all the way out to 81 before it reaches 4. Okay? So there's our log parent function. Yes? I'm listening. Growth and decay. We don't necessarily have a growth or decay label that we place on it, but the curve can go both ways. So it can go like this with certain bases. If the base had been 1/3, it would have gone like this. Okay? So I just want you to notice one thing. This is the exponential function that we've used in the past. This was its asymptote. The asymptote for our log function was this. This graph had the point 0, 1. Our log function has 1, 0. This graph had the point 1, 3. Our log function has 3, 1. This graph has the point -1, 1/3. Our log function had 1/3 -1. What is the relationship between y equals log base 3 of x and y equals 3 to the power of x? They are not reciprocals, not opposites. Inverses. Good. Okay. All right, so these are inverses of each other. All right, so tonight's homework in this section will ask you to do some log calculations. It will ask you to rewrite things from log form to exponential form. So they'll give you all the pieces, just can you rearrange them right to be exponential or logarithmic. And it will ask you to graph, and we need to eliminate a few problems because we're going to make sure we're not doing any of these ones in this homework, just the parent function ones. Okay? So I'm going to go ahead and give you which